how MIFARE Classic got broken again.
So, yeah, that's a topic that get a bit hype in the summer news. I don't know how many of you saw it in August. It gets a bit out of hand over there because initially that was just a paper for the research community. But yeah, okay. Let's talk about it. Don't expect too much technical details out of the talk because there is really a lot. But by chance, there is also a paper that you can find on ePrint, which is pretty large, that goes over all the details and that I maintain. For now, it's version 1.1, but I will show you a few more things. That's what's published. So after my talk somewhere, I don't know, tomorrow when I have a bit more time, I will update a new version with the latest tips and tricks. So, yeah, breaking MIFARE Classic in 2024, that sounds a bit strange, huh? Right? Like, who's this guy with this, it was broken years ago, no? So, I will have to explain a bit the past things, just that we understand a bit more where we stand today. What's MIFARE Classic, just in case some of you don't know? So, we are talking about RFID tags, which are used everywhere, like on all these hotel badges. It's a memory chip. That's, you can see the layout over there where you have some data, like here and there. And you have also special sectors because it has a few security features, to provide mutual authentication between the tag and the reader, and to be able to, encrypt also the communication once you are authenticated between the reader and the tag. So these fields are used usually to type your keys, and we call that usually the slot for the key A and the slot for the key B. And you've also a few bytes in the middle that define the access rights of both keys, so that you can configure your stuff such that, I don't know, key A can write on the stuff there, but key B can only read. And my handwriting is horrible, I'm sorry. So there is some crypto behind that. I will not go on that part because it's really quite horrible to explain. But basically it's a stream cipher where you inject some keys and then also like the UID and some random nonce that comes from the tag and the reader. And at the end, you have a stream cipher which is initialized on both sides with the same material, so they can both derive the same, what we call key stream, like just an infinite stream of random bits. And when you XOR your messages that you're exchanging between both sides, they can be secured. What's more interesting is the protocol that is using this crypto cipher. That's how you initialize it and get mutually authenticated. So basically, the reader interrogates about what are the tags around. The tag reply with on UID. Then the reader sends a command to say, okay, I want to authenticate to that block because MIFARE Classic, you cannot read before being first authenticated to a block. So you say with key A or key B. Then the tag, it generates which it's called a nonce. It just means it's a random number that comes from the tag. That's why there is a T, sends back to the reader. The reader performs some function on it, and it generates its own random and packs everything together back to the tag. And this part is already encrypted with the partially initialized stream cipher. The tag can then decrypt it. It does the same operation. It says, okay, is my AR the same as the one I got from the reader? If yes, the tag has authenticated the reader. And then it performs some other function so he has its own answer to send back to the reader. And the reader can also perform the same operation and say, okay, is it well the answer from the tag that I expect? If yes, then the reader has authenticated the tag as well. And then they can talk together. The reader can say, okay, I want to read that data, write that data, and that would work. That protocol we will go over and over during the presentation because every attack that we have are always on this protocol. There is a variant of the protocol is that when you are already authenticated to one block and you want to read another block from another sector, it means it has other keys. So you have to authenticate again to the new block. You can just stop and start again a new session, but you can also jump directly from your existing session to the other one. Then it looks like that. There are a few differences over there. One is that the command that you send to authenticate again is encrypted because we are already in an established session. And a little funny thing is that the nonce that is sent by the tag is also encrypted, but you see here it's in green because it's encrypted with the new key of the other sector you want to go through. So when you are in crypto, you say that's already a bit strange that I get something from the tag encrypted with a key I didn't prove I know yet, because it gives already some information possibly to an attacker, and we will see that there are many attacks around there. So the timeline, I think the first tags were around 94. They were made by Philippe at the time. Then becomes like a Philippe Semiconductor, became NXP a few years later. Infineon got also the license to produce MIFARE classic compatible chips. And then we will also talk about the chips made by Fudan, which is the biggest Chinese manufacturer of RFID tags, or at least HF RFID tags in China. And I think they started somewhere in 2004. At least I found the datasheet version 1.0 of that year. So should be somewhere around there. Then 2007, 2009, that were the dark ages of MIFARE Classic, because we got many papers there that broke a bit everything. I will only discuss about 4 of them very quickly. Everything started with actually the hardware reverse engineering of the MIFARE Classic, because so far nobody knew exactly what was the crypto running on that. It was fully proprietary. So there was a talk at the CCC that explained how they reverse engineer to the gate level, to the transistor level, to go back to the understanding what was the crypto over there. And that helped everybody else then to build attack on that once they saw how crappy the crypto was there. So we got the dismantle MIFARE Classic. That one explains that basically if you are like eavesdropping the communication between a reader and a tag, which are both from the same system and they both know the key, it's enough to break instantly the key. So yeah. That protocol was not that good, visibly. And by the way, if you're using the Proxmark and you're sniffing and you're looking at the trace of the communication, it does it for you. It directly dumps you the clear text of the communication and which key was used. Pretty handy. We're still using this kind of attack when on some type of tag we need a first key to then attack the other keys, and to get the first key when you are really blocked with some cards, you just go to the reader with the card and you sniff it and you can get it. Even, well, kind of worse, without the tag, you can just go to a reader, pretend you're the tag, just send your own NT, just random stuff, you don't care, and you see what the reader replies, which is already encrypted with the key you want to break. Do that with twice, and just with 2 traces, same thing, you can just break the key. Very convenient, and we will use it later as well. Then another one, dark side of, okay, for short, we call it the dark side attack. That one, it relies on not only vulnerabilities of the crypto block, but also vulnerabilities in the implementation of the thing on the tag. And a few implementation errors were like, these random nums, you can make it repeatable. If you pay attention to the timings of your request, you can get several times the same nonce, which is nonce means only once normally. So you just send it to the reader. You are the reader, sorry. So you talk to the tag. Tag sends you some nonce, and you don't know the key, so you don't know what to answer. So you just send garbage to the tag. Normally the tag, when it doesn't see the proper answer from the reader, it should not reply at all. And if there is no reply, there is nothing to work on. But there was also an implementation error where internally, if the parity of the random stuff being decoded was matching, the card was still replying with a NAC, so not acknowledged, which was encrypted. And then, okay, that's something you can work on. And this cryptograph describes that if you do that like 8 times in total, you can again get the key. That reply, you don't have it always, because here you have like 8 bytes, so you get 8 parity bits, and so you have only one chance over 256 that you get a reply. So it's 8 times total, but you have to try multiple times to get some answer from the tag. That's the dark side. Then we got also another attack described in the YC Pocketing MIFARE Classic Card paper. This is a nested attack. That one, it's using the variant of the protocol where you already know a key. So the first attack is handy to get the first key. Second attack is handy to get the other keys because it's much faster than the first one. That one has also, it works also on some other implementation vulnerabilities, is that this nonce can also be predicted if you're very strict on your timings. Actually, these nonce, they come from some state machine which is looping on itself quite often. And if you just let it run and you look at very precise time, you can predict its value. And actually, the nonce should be 32-bit, but it comes from a state machine which is only 16-bit. So actually, when you know half of the nonce, you can know what is the other half, which helps also on the attacks. And all in all, you do that 2-3 times and you can break the key as well. So, was it the end of MIFARE Classic and everybody migrated away from that crap? Unfortunately not, because the reality is that the solution to migrate off that were pretty expensive, and changing all your readers everywhere in your hotel or so are really a big cost compared to what is the risk if someone break my key. So NXP at the time, they made the MIFARE Plus, which is a card that is a kind of hybrid to help people to migrate from MIFARE Classic because it has 3 security level. And on the first security level, actually, it's just MIFARE Classic compatible. And the idea behind is that, okay, it let you some time to do your migration because you can handle these keys. And when you touch all your reader, then you can go to a security level 3 where you are using ASCII, for example, and things become secure. But it was not very popular, again, costly. So I think a few years later, they say, okay, everybody is still using MIFARE Classic. We still have to do a little something for the MIFARE Classic. So they created the MIFARE Classic EV1. And these two, they still try to make it a bit better because they fix all the implementation issues. The protocol issues, they could not, otherwise it's not compatible anymore. But the implementation issue we saw before, they could fix them. That means, for example, that the nonce from the tag, now you get a really, truly 32-bit random. And of course, you don't reply to the reader at all if the reader sends you something which is not correct. So we're safe here, and that's what they call the hardened cards. So are we safe there? Were we safe there? No, because just a couple of years later, yet another paper came out, which is about cryptanalysis of this hardened MIFARE Classic card. And they came with an attack which is called hard nested, because it's a nested attack against the hardened card. Nested means that you still need the first key. So either it's a key from the dictionary, or you need to go to the reader to fetch a first key. Once you have a first key, you can play this hard nested attack. And why is it still possible to get some crypto something you can work on and break it? Is because there is something I didn't talk about yet. Is the parity bits of the nonce. And the parity bits, normally you put that on top of your transmission. So you have your encrypted data and you can just add some parity bits. for safety in your communication. But here the parity bits were computed on the plain text, not on the ciphertext, and the parity bits themselves were encrypted. And worse, they were encrypted with some bit of the key stream that were reused for encrypting other stuff. But key stream, by definition, you're not supposed to reuse it. It's like the XOR or the one-time path you heard about. If you're using your one-time path twice, problems. Still, you have very little information. Actually, you've only 3 parity bits that you can use for every request. But these very smart guys, they found out that by making quite many requests, you can still break the key. In practice, this takes, I think, like a minute to break one key. Now you have 32 keys on a card for 1K card, which means it can take still like half an hour to really break all the keys in the worst case. Then came topic of this talk, the static encrypted nonce card, and I will explain why it's called like that, static encrypted nonce. Later we found that they were actually cards made by Teuwen. So static encrypted nonce, that was more like a nickname given by the community on this card that we could not break. And later we figure out that they were actually the secure version, so you have an extra S of this other card actually. They started appearing 2020 and they become really incredibly popular when you start poking the cards around in the hotels and stuff like that, because they are much cheaper actually than the official cards, and they are actually more secure because I'll show on the next slide that they protect against all known card only attack. Card only, that's, I mean, like I'm in the metro and I try to dump your cards, and you find them everywhere. Like it's a hotel in Paris, this one. This is, Den Haag, last year, hardwear.io hotel. That's a Nulcon Goa hotel card. Same thing, still the same. That's a hotel I was on holiday in Spain. That was physics, music festival found this summer. So really, it's not just that you find them in China. You find them everywhere today. Especially for the big consumers like hotels, festivals, they have to buy many of such cards and then just go for the lowest price, and that's it. So why are they resisting to all known cards, even better, all known attacks even better than the hardness cards? Is because, of course, they don't reply to the reader. That's easy to fix. But rather than a fully random nonce, they chose to make it static. Which means, you remember, we need a few thousand times a different nonce here. Well, if you try again, you just get the same nonce again and again and again. It's a kind of weak nonce because it still comes from this state machine I was talking about. But finally, you can talk as many times you want. For a single key on single sector, you always get the same nonce. So you have to work with it, and there is no possible attack so far on that. So that's where we stand. I was not really looking to this card actually for the past years, but the community did, and they found already some properties of these nonces. And they figure out that static nonce, it's not always strictly the same. Actually, is the same for one authentication request. So for a specific sector, on a specific card, you have a specific nonce value that depends actually on the key which is written on the card. So if you change the key on the card, the nonce that you will get is different. But yeah, that's it. At that point, still nobody could do anything with this card. So the first idea I got was we need more nonce. So how can we get more nonces for the same key? Well, actually, if the same key is used on different sectors or even different cards, we will get different nonces. And that's good enough. Because there are weak nonces, if we get 2 or 3 of them, we can already mount some attack. So let's assume that the key is reused on different sectors of the same card. And that's what I call this reused key nested attack. So how it works on the protocol, at the stage, pretty easy on the protocol level. And you just make a request for block X, and then block Y, and then block Z, and you hope that they share the same key. You don't know, you just try. With two sectors using the same key, we get a few thousand key candidates, and then we can try them online on the card, which take quite a while, and you don't know, maybe it works, maybe not. If by any chance a third sector is also using the same key, the key candidates intersection will be like just one key, and then with just three sectors using the same key, you can break the key. That's already something. It's not super satisfying because it works only on quite specific cases, and you don't know if there are any keys reused on some of the sectors. You don't know which sector, so you still do to try a bit all of them. But at least now we have a way to break some of the keys. Then I wanted to find other ways to get more nonces. Even if the key is not reused, can we, I don't know, do some operation on the card, like I authenticate and then I read, I do some other stuff before the second authentication, and maybe the nonce I will get will be different. So I did some lightweight fuzzing about the existing commands and about a bit of borderline undocumented commands to see how it would react. And what I got was the following. So actually the authentication command is just 2 bytes. It's a 60 for key A, 61 for key B, and then a number which is the block you want to authenticate to. And actually I tried all the other values, 62, 63, 64. I tried also many other things, but just explaining what worked. It will be faster. And for some of the values, actually, I still get the same nonce, and I can still authenticate with the same key. So they are like equivalent commands. I don't know if there are any functional differences between these commands. And for 61 is for key B, but also the 3 other ones, they also work for the key B. And I get that nonce. Now, if we look to the other ones, suddenly we find strange stuff, because we get, another nonce. That's what I need. But that doesn't work neither for key A or key B. I can't do anything with that. So I say, what's going on? Maybe there is another key. How can we know? Well, if it's another key that is reused in other sectors, well, we got our brand new attack. Let's try on it. The reuse key nested attack. So we just ask with authentication 64, that doesn't exist normally. You get something, and then you go on another sector and another sector. So you get 3 sectors. You hope it's the same key. And it worked. And I found that key at first. That was valid for the 3 sectors I was looking at. Then I tried that key on the other sectors. It was working on all sectors. Then I took my other tags and I looked and, it works on all the tags I have for the S version, at least. I guess that's what we can call a backdoor. So let's try to demonstrate what you can do quickly with that, without even trying to break more keys. Here you have to help me a little bit because I don't see that screen. So normally there is a console over there. And normally if I do that, and I will try script run demo 1. And demo 1, it's polling. So now it's blinking. I will remove so you see easier what's happening. And it's polling for a card. When it finds a card, it will just read the data with the backdoor key that we found and display it. Okay, let's try. Bam. It's 1 second, 2 seconds. You can see, okay, I don't see my mouse there anymore, but you see that you have the data blocks. Yeah, it's no sense for me with the mouse. Okay. But the yellow stuff, that's the keys. And the keys, actually, that's the only thing that you don't see. Because the backdoor allows you to read, not write, unfortunately, just read data. And only the data, not the keys. So, okay, we got something that allows to kind of dump the card, but just the data, not yet the key. What can we do? Slides are back? Yeah. Okay, thank you. So, at that point, it is a bit strange because we know a lot of attacks about MIFARE Classic, but every time we had the data of a card, that's because we knew the key. Because you need the key to read the data. And now we have some data in hand and not the key, and say, can we already do stuff with that? I guess in some situation we can already do things, because like in your hotel, if the data block are maybe encrypted for your room, but in a way which is decorrelated from the ID of the card and the MIFARE Classic layer of the card, I can just dump the data of someone, break my own room card, because then I can go to the reader of my room, whatever, and write his data on my card, and maybe that's good enough. Or if you're visiting an enterprise, a company, and you are a visitor badge, maybe you just pass 2 seconds on someone else's employee's badge, and maybe same thing, you can just swap the data, and maybe you can already do things. But we can also do something with the attack we saw previously, the reader-only attack. Because the reader-only attack, usually we talk only to the reader, and that's to find a key, and then we go back to the tag, and we can try to read the data of that tag with the key. But now we have already the data. So it's easy. We just go to the reader, wait for the reader to authenticate to a block. It will fail because we don't know the key, but after 2 attempts, we know the key, so we can emulate the tag with the proper key. Then the reader will authenticate to it and wants to read data and say, yeah, sure, I already have the data. Here it's, so you can immediately, so you go first to the tag of someone, 2 seconds, then you go to the reader, talk 3 times to the reader is happy and has the data it wants. There is a limitation there. You can't do also support for nested attack at this, nested authentication at this point, but for a single read, that works. So if I try that now up here like that, what do you see? Previous demo, perfect. Now I can script run demo 2A, I think. So what I will do now is that I have a tag that contains unknown keys and unknown content. Well, the unknown content, you already saw it. I will read it, and that's done. We know it takes just a second. Now we are able to emulate that card, which is normally there. So now it's running in emulation mode, and I will take another reader and I'll try to show you the screen of that reader, which should be that one. Yeah. And now if I try, what does it say? It's fail? Yeah, of course. I have to put it on top of my emulation. Okay, let's try again. Authentication error. Yeah. Second time, authentication error. But maybe you saw something on the other screen that it broke the key. So the third time works. Yeah? With the right data. So that's a type of attack that was not possible before, but now we can do. Cool. Okay, back to this one. Yeah. Now would be still interesting to actually break the keys on the tag itself, like to make Then you can make a real clone of the tag. To do that, so you remember the different nonces that we got for the different unknown commands that we had so far? So now we have the key. So for key A, key B, we can decrypt the nonce that we get, and we can get some values there. But now we know the key that was used for these other strange commands. And if we look at the clear nonce, so the nonce were different because they were encrypted with different keys. But now that we decrypt them, we realize that the nonce is actually the same. They were just encrypted differently. So that's nice. Now what can I do? I can authenticate with the backdoor, with an extension that corresponds to key A or key B, decrypt the nonce, and then do some attack on key A and key B, because now we know the clear nonce. We are not just working with an encrypted nonce that we can't do anything. We know the clear nonce. We can get the encrypted nonce, so we can XOR them. That means we have a part of the key stream, and that's broken crypto one. When you have a part of the key stream, you can roll back to the key. So that's what's displayed here. So I repeat, authenticate with backdoor. We get an encrypted NT that we can decrypt. Then try to authenticate to the key A. We get an unencrypted version of the nonce, but encrypted with key A this time. When we have that, we have about 32 bits of key stream. That means there is still 16 bits of the key which are unknown. You can play with the parity, so divide by 8. So you have a few thousand key candidates, and in a few minutes, you can try them all directly on the tag and break the key. So now we have an attack where there is absolutely no prerequisite. You don't need to know a key first, because you know a key, and that's a backdoor. Let's use it. And you don't have to have the key being repeated on different sectors. You don't need that assumption anymore. It works with 32 random keys. It's still quite long, because you see you've many candidates to try on each key. So the total attack would take about 2 hours, I think, to copy a card, but at least that's the first time that you can copy such a card. We will optimize that a bit, but before going to that, let's see if we can also improve the data first attack that I presented just before with emulating the card toward the reader. We could not support the nested attack, the nested authentication, because that means we would have to send some random nonce to the reader that are supposed to be encrypted. The reader decrypts with a key we don't know, so the nonce could be anything. You don't know. But now we saw that we can decrypt that nonce. So we know the clear nonce, and with that, if we do the same with the reader, so we can already do the first phase, that's the demo that I just did before. But if the reader wants to authenticate to another block, you just send the encrypted nonce that you captured from the tag, and which is static. That's the idea of all these static encrypted nonce. And for that one, you know already the corresponding NT. So with this information plus the attempt of the reader, it's enough, you get the key directly. And if the reader wants to read a block, no problem, you have the data, same thing. So now we have an attack where we go 2 seconds on a card of someone, we collect the data, we also collect all the nonces that we decrypt, so we have the clear nonces, the encrypted parity. We still don't know the key, but we don't care, we go to the reader, and whatever the reader is asking, we can just break the keys on the fly, maybe with a few retries, because we need a bit of time to break that key and represent, a bit like what we did the first time, 2 errors and then it passed. But yeah, we can completely fool the reader, and that's good enough. Still back to the really tag-only part, where we would just want really to get the key out of tag without having to go to the reader. at some point, if you want to clone the card tag, is to go to the reader. Otherwise, what's the point? Huh? But okay, if you want still to be able to make a copy of the card and not emulation with expensive Proxmark and stuff like that, can we do something a bit better? Huh? We have a 2 hours attack. Okay, so I try to reverse engineer the way that this static nonce is constructed, because it depends on the key. We change the key, we get another nonce. How is it related? How does it change? That part is a bit of a black magic, and I will not explain it here. It's a bit explained in the paper. If you, with a few beers tonight, I can go a bit more in detail with you, no problem. But the idea is that when you know already the nonce for a certain key, you want to go to another key, I can tell you what is the nonce. And it's not trivial. It involves like, I end up with 4-bit S boxes and nibbles of the key being injected and different cycles of this LFSR. It's really not trivial. That's why I won't bother you with that here. But with this relationship, we can do interesting things. We can make a faster backdoor attack, because now when we have these key candidates for key A, for key B, we can see which ones are related with this relation I showed you. And it reduced the key sets by a third, so factor 3 in terms of speed for the attack. And when we have one of the key, A or B, we can find the other one immediately, because this relationship has to hold. I won't show that one here, but you get the idea. Another way that we can also optimize the attack, and by the way, the other one I said 2 hours, now it's 6 times faster, so it's like a quarter to 25 minutes to dump a card that has really 32 fully random keys. There is still a trick that we can do also to make it faster, is what I call there the light fast supply chain attack. So supply chain, you are the vendor of the tag. If you are the vendor of the tag, you can already read all your tags, which are with the default keys, get all the nonces. And when people will configure these cards, they will change the keys. But you already have half of the relationship I showed you. You already have a nonce and a default key. So when you want to know what is the other key, you can use that relationship to filter your key candidates and break the key very fast over there. So for that one, I don't know if I've enough time to show, but yeah, I can show you maybe first. Where is this? It's here. Is it still emulating? I don't remember. Press stop. Yes. Clear the stuff. So actually we get a script that automates a bit all these these attacks. FM11 RF08A3 3, and now I'm not showing the screen. Sorry. H, up. Yeah. Okay, good. So with that script, for example, okay, I'll take directly a tag which has already 32 random key, and so you see, getting the nonce, it takes 2 seconds. We know that. Then we are computing all the possible key candidates, dictionaries for each of the key, which takes about 15-20 seconds. And then, as such, if we try, because there are 32 random keys, it will announce that it takes about 15 minutes. We will not wait for that time. So you see here about 15 minutes for completion. Okay, that's too much for us, but we have this supply chain attack. So here we are just giving an extra file, which is mentioned there, this default nonce stuff. And default nonce stuff, by the way, it looks like that. It's very short. It's just the nonces that correspond to the default keys. And with that, we can let the attack run. So the first phase takes about the same time, about 20 seconds. But once we're there, We don't need to wait 15 minutes anymore. A little bit, up, and now, all the keys are being dumped like that. And for those who read the news, that story of backdoors that doesn't stop there, because of course I looked also to the previous generation of the tags. So the previous version generation has also the backdoor commands, but the key that was not working, so I had to break that other key. But they are susceptible to the nested attack, for example. So it was just a matter of adapting the nested attack to the backdoor command, and yet another key. That version is the 4K version of the Fudan, and it has also yet another key, easy to break. Then when I started sharing my results with the Discord RFID hacking community, some people helped and say, oh, I have a version which is a 7-byte UID of that one, and we get the same key as the secure version, because this is the secure, there is a typo there. This is a secure version, 7-byte log. So again, the same key that we saw before. There is also this FM1208. It's actually a CPU card that emulates MIFARE Classic, and that's the same key as the old Fudan. Strangely enough, someone found a secure version, so the new version, but still with the old key, which is a bit weird if you roll out a new product and you want to change the key because it could be broken by the previous version. You just don't already use that one. But we got only one sample with that. And then, more intriguingly, we have also the same backdoor on very old cards of the official manufacturers. That's Philippe cards. This is Infinite card. And we have the same backdoor, but the same key. I don't have answers. If you do, please, please come to me. If you want to go further, there are many, many resources available there. You have first this ePrint paper I was talking about, and I will update it with the latest tricks that I showed here for the demos. It was done also, all that part on the Proxmark, so all the proof of concept scripts were developed there. I think I've pushed 7 new commands to script whatever on the iSmart 4 repo. And also updating existing commands to take into account the possibility to use the backdoor. Little harder because, all was possible. I mean, a lot of RFID research, maybe all of them, I don't know, are really made possible thanks to the incredible work of Iceman on the Proxmark. And I'll show you a snapshot that he showed 2 weeks ago. Look at these numbers. So he was active for the last 10 years of the project, and he reached 10,000 commits. That's 3 commits a day on average. It's an incredible job. So big shout out for him, please. Then, people say, okay, Proxmark is a nice research tool, but I have a Flipper 0. What can I do with the Flipper 0? So thanks also to Nathaniel to make the porting of everything that was done on the Flipper 0. It's almost on the official firmware, or it's already available on the multiple alternative firmware. And of course, if you want more information, just join us on the Discord. And I don't have time for conclusion, but honestly, I don't have big conclusions there. Just stop using MIFARE Classic and stop buying cheap stuff because it looks, it's cheap, nice. You may have more problem than you think. And, about these old backdoors. Does it matter? Because old cards are already broken. But go back to the timeline. That means that at some point between 94 and 2007, that way for you, you thought that was super secure card. Still, someone knew the backdoor and could do stuff with your cards, which is a bit disturbing. Like for 14, 15 years, it was like that. So yeah, still think about that. And I'm done. Thank you.
We're a little bit over time. We will still take 2 quick questions, but before that, a quick announcement. There is the networking party at 7 p.m. For those who are invited, you should have gotten an email with the location. Yeah.
Thanks for the incredible work. Bravo. You don't have the answers, but you have an opinion of what was the purpose of this backdoor?
I don't have, for myself, satisfactory hypothesis, because some people say, yeah, backdoor can be just debug stuff that are left over. But what do you debug there? The only function is to read the data the user are putting there. Debug would be useful, like if you write a wrong access control and lose access to the card, you could reset them, but that's not the case. It's just giving access to user data. So debug, I don't believe it. Now for operational work, it could be easier. I mean, if you can read the data, why can't you just read the key and you're done? So it's also not very satisfactory. And then who did what when you see it was on these old original cards and then the Chinese, it's strange. The Chinese copy it without knowing. But then they figure out, they say, oh, it's handy. Let's rekey it for the next one. I don't know. So many really weird stuff are going there.
All right. Thank you.
All right. One last question. Do you have any question? Okay, then let's thank the speaker again.
Thank you.